There is a paint that cools buildings below the temperature of the surrounding air using zero electricity. Not a little cooler. Not keeps the heat out cooler. Actually colder than the air around it, in direct sunlight, in the middle of the day. Stanford confirmed it. Purdue proved it works at scale. A bucket of raw materials costs roughly $15 to cover an entire roof, and most Americans cannot legally put it on their homes. This is the story of the cheapest cooling technology ever invented, the people who proved it works, and the industry that is spending millions to make sure you never use it. In 2014, a professor of electrical engineering at Stanford named Shanhui fan asked a question that changed the trajectory of building science. What if a surface could reject the sun's heat so complete that it actually radiated energy away from a building faster than the environment could heat it up? Not with insulation, not with reflective metal, with a material engineered at the nanoscale to exploit a loophole in the laws of thermodynamics. Fan and his team built a multi-layer film of silicon dioxide and hafnium dioxide, each layer tuned to a precise thickness. When sunlight hit the surface, 97% of it bounced back. But the real trick was what happened with the heat the surface did absorb. Instead of warming the building, that energy was emitted as infrared radiation at a very specific wavelength, 8 to 13 micrometers, which corresponds to the atmospheric transparency window, a gap in the sky where the atmosphere is essentially invisible to thermal radiation. The heat passed straight through the air, through the clouds, through the upper atmosphere, and radiated into outer space. Outer space, which sits at roughly 3 kelvins, is the only natural heat sink colder than Earth. Fan surfaces stayed 5 degrees Celsius, 9 degrees Fahrenheit, cooler than the ambient air even under direct noon sunlight. No compressor, no refrigerant, no electricity, just physics. The problem was that Fan's original film was expensive, difficult to manufacture, and impossible to apply to a real roof with a roller and a paint tray. That is where Xiulin Ruan entered the picture. Ruan, a professor of mechanical engineering at Purdue University, set out to turn Fan's laboratory concept into something a roofer could actually use. His team experimented with dozens of particle compositions before landing on barium sulfate. Barium sulfate is not exotic. It is used in medical imaging, in paper coatings, in the pigment for cheap white house paint. But Ruan's team engineered the particle sizes to vary across a specific distribution, each size scattering a different wavelength of sunlight, so that collectively they reflected 98.1% of all incoming solar radiation. The resulting paint looked like ordinary white paint. It went on like ordinary white paint. But it generated 113 watts per square meter of cooling power. In outdoor field tests conducted by Purdue, surfaces coated with this paint dropped nearly 2 degrees Celsius below the ambient temperature. No other paint on the commercial market does this. Ruan's formulation used particle fillers, primarily calcium carbonate and barium sulfate, that cost less than $1.50 per 100 square meters. At scale, this paint is absurdly cheap. The $15 figure is not marketing, it is materials science. Stanford did not stop either. In 2023, Fan's group published a follow-up that solved the last remaining practical objection: color. Their 2-layer system placed a thin, infrared transparent colored top coat over a radiative cooling base layer, allowing buildings to appear in conventional tones while still rejecting heat in summer. But they went further. By engineering the top layer to switch its infrared behavior with the seasons, they created a system that keeps heat out in summer and traps it in winter. Stanford ran building energy simulations on a mid-rise apartment complex and found that the year-round HVAC energy reduction hit 7.4%. Summer air conditioning costs dropped by roughly 21%. The winter mode version cut heating energy by approximately 36%. The estimated carbon dioxide offset reached up to 539 pounds of carbon dioxide equivalent removed per square meter applied. These are not projections from a startup pitch deck. These are peer-reviewed numbers published by one of the most respected engineering programs on the planet. So why is it banned? The answer starts in the places where 75 million Americans live, communities governed by homeowners associations. Homeowners associations control what color you paint your house, what materials you put on your roof, and whether your property conforms to the aesthetic standards of a neighborhood covenant drafted decades before anyone imagined paint that could cool a building for free. Many homeowners associations explicitly ban stark white roofs. They mandate earth tones. They require non-reflective finishes. Architectural review. Committees, small panels of volunteer neighbors, can reject any roof treatment for aesthetic reasons alone. No scientific justification is required, no cost-benefit analysis, no energy audit. If a committee member thinks white looks wrong, it is rejected. A handful of states are pushing back. California and Florida have passed laws overriding certain homeowners association restrictions when energy-efficient materials are involved. But most states offer zero protection. A homeowner in Texas or Georgia or Ohio who wants to coat their roof with the most effective cooling technology ever invented can be fined, sued, or forced to strip it off because a neighbor on a committee does not like how it looks. But homeowners associations are only the visible barrier. Behind them sits something far more deliberate. The EPDM Roofing Association represents manufacturers of ethylene propylene DNA monomer, the black synthetic rubber membrane that covers millions of commercial and industrial rooftops across the United States. Its members include Johns Manville, Carlisle Syntec, and Elevate. These companies have spent years lobbying against cool roof mandates, and their track record is remarkably effective. In Tennessee in 2025, industry lobbyists persuaded state legislators to repeal a reflective roof requirement for commercial buildings, a rule that had just been expanded to cover Nashville, one of the fastest-growing and hottest cities in the Southeast. In Denver, EPDM advocates killed a cool roof ordinance outright in 2015. A weaker version eventually passed 3 years later, diluted to the point of near irrelevance. When the American Society of Heating, Refrigerating, and Air Conditioning Engineers proposed expanding its reflective roof standards into cooler climate zones through a code change in ASHRAE, the EPDM industry blocked it. Ellen Thorpe, a lobbyist for the industry, stated publicly that they have been able to stop all of those mandates from creeping into climate zones 4 and 5. She said this openly. On the record. The strategy is not hidden. It is simply unreported. The industry's preferred counter-narrative is that cool roofs cause condensation and mold, that reflecting heat away in winter increases heating costs to the point of negating summer savings, and that white roofs degrade faster than dark membranes. These claims have been tested. Target, the retail corporation, conducted an internal study across more than 24 of its stores that had been retrofitted with cool roofs. They found zero evidence of condensation problems. Zero evidence of mold. The heating penalty argument is directly contradicted by Stanford's 2023 dual-mode system, which reduces heating costs, not increases them. And the degradation claim ignores the fact that barium sulfate is one of the most chemically stable compounds available, resistant to UV breakdown, acid rain, and biological fouling. The regulatory environment compounds the problem. Many local building codes still reference outdated roofing standards that were written for materials like asphalt shingle and tar paper. They do not account for radiative cooling. They do not have a category for paint that performs as well as mechanical air conditioning. Earlier formulations of radiative cooling coatings did have legitimate regulatory issues. Some used volatile organic solvents, including toluene and dimethylformamide, which triggered VOC regulations and raised valid health concerns during application. But newer water-based formulations have solved this entirely, achieving VOC levels as low as 18 to 30 grams per liter compared to 200 grams per liter for standard architectural paint. Building codes have not caught up. The paint is cleaner than what is already on your walls, but the code does not recognize it. Titanium dioxide, a common pigment in conventional paints, requires energy-intensive mining and processing. Barium sulfate must also be mined, and critics argue that at truly massive scale, the mining carbon footprint could partially offset energy savings. This is a legitimate concern worth studying. It is not a legitimate reason to ban the technology while permitting every other mined building material on the market. California's Title 24 Energy Code already mandates cool roofs for many commercial and multifamily buildings. The state proved years ago that reflective roofing technology is policy-ready, enforceable, and effective. Buildings in compliance use less energy. Full stop. If a regulatory framework can work in the largest state economy in the nation, the argument that cool roof standards are impractical falls apart. Several companies are currently in active negotiations with Purdue University to commercialize Ruan's paint formula. A newer thin-coat version, applied at 0.15 millimeters, compared to the original 0.4, opens the technology to surfaces beyond buildings. Cars, trucks, shipping containers, freight trains, data centers. Every surface that currently absorbs heat and requires energy to cool it becomes a candidate. Consider what this technology actually represents when you strip away the regulatory battles and the lobbying. Every square meter of radiative cooling paint applied to a roof is an AIR conditioning unit that never gets purchased, a compressor that never cycles on, a refrigerant charge that never leaks hydrofluorocarbons into the atmosphere, a transformer that never strains under peak summer load, a power plant that never fires up its peaking turbine. At scale, widespread adoption could measurably reduce urban heat islands, those pockets of superheated air over cities that kill thousands of people every year, most of them elderly, most of them poor, most of them without air conditioning in the first place. This paint does not just save money for people who already have AC, it could save lives for people who do not. The $15 paint that beats air conditioning is not a prototype. It is not a theory. It is not awaiting some breakthrough. It works. It has been tested in the field. It has been validated by two of the top engineering programs in the world. The raw materials are abundant and cheap. The application process is identical to painting a wall. And it is being kept off roofs by an industry that profits from keeping those roofs dark, by codes that have not been updated in decades, and by neighborhood committees that prioritize the color of a shingle over the temperature inside a home. The question is not whether this technology works. Stanford confirmed that years ago. The question is how long we will allow the people who sell the problem to prevent us from using the solution.